everybody. We're the Printer International team. I'm Kevin Sharma. This is Laura, Chen, and Melanie White. And today we're going to tell you a little bit about our project over the course of the semester.
So to quickly go over our agenda, we're going to refresh you on what Printer is, the components of sales that Maggiano looks at, the problem we have, our analysis, our approach, the revenue formula that we use, our final model, and then our proposal for the next fiscal year, and the pricing app that we came up with, and then questions. So to give a quick recap, Maggiano is a division of Printer International. We are defined as a casual dining restaurant chain. We have about 50 locations across the United States, and we work directly with Michael Breed, who's the Senior Director of Marketing. So our project might look a little different from the project that we introduced at the beginning of the semester, because we changed directions halfway through. So this is a completely different project from the one that we introduced. And quickly, we're going to go over the three components of sales that Maggiano looks at. So the primary goal of any restaurant is to increase sales and profit from year to year. And the first component is price, whether usually it would be increased from year to year. And 100% of each price increase goes towards the bottom line. For example, if an item was increased a total of $1 from this year to the next, that 100% of that dollar goes straight to profit, because the customer is still buying the same item, getting the same service for just paying an extra dollar. For traffic, that is the flow of customers coming in through the restaurant. It's a big measure of how healthy the restaurant is from year to year. So if traffic increases, that's a sign of a healthy restaurant. However, with traffic, only 45% of that flows to the profit, because for every customer that comes in, there's a variable cost associated with it. And then mix is what the customer actually buys when they're in the restaurant, and it's changed or it's affected by promotions such as the buy one pasta get one free. So it's much more difficult to quantify its impact on sales. So which is why our project focuses on pricing and making sure that it's the most efficient in order to increase sales throughout the year. So before we go on to our analysis, we were given several constraints and assumptions to work with. First off, our constraint was that we were only given the past few years' data of demand, sales, etc. And we were also told to keep our price increases from 1 to 2% across the entire menu. We also had to minimize the number of items that were increased on the menu, so, whether by total or by section. And then finally, classic pasta prices were not to be changed. And then some assumptions that we had starting off was that historical demand was indicative of future demand, so that we could work with that data. There was no current system in place that they were using to estimate price changes. And then restaurants were also kept at the same price level across the United States. And then finally, we used the assumption that when prices increase, demand decreases. So we worked off the theory of elasticity, which Melanie will talk about.
Thanks. So again, what we're trying to do is increase the total menu price for Maggiano is about 1 to 2%. They make these changes about semi-annually. So they don't have a mathematical procedure for making these price changes. So in order to give them something to work off of, we focused on the theory of elasticity. So a little background on the economics behind it. If a product is inelastic, it is independent of the price. So such as gasoline, it doesn't really matter what the price of gasoline is, we're still going to put it in our cars, we're still going to go to work every day. Where elasticity is the horizontal line, which is dependent on price. So these are luxury goods. And so when we are experiencing maybe an economic downturn, these goods are severely affected. So we focused on the demand elasticity that we saw in the restaurant industry, which was a negative demand elasticity. So that means when price goes up, demand goes down. So our approach began with this fundamental idea, and the way we found this was we took our data that we were given and started with percentage price increases from month to month. But to take care of seasonality, we did, for instance, December 2012 compared to December 2013 to not incorporate any seasonality within the year. So we took the percentage price changes and the percentage demand changes, and then ran linear regressions between the two of them to find this demand elasticity. And our hypothesis was correct. The majority of them were negative. Some of them weren't, and those were very, very small numbers away from zero. So from that, we created a revenue formula that incorporated this demand elasticity as well as the percentage price increases and the demand percentage decreases. So the reason we did this was to find the point of diminishing returns. Our theory behind this was if we found where revenue kind of capped or peaked, we would be able to give a ceiling price for all of the menus across, or for all of the items across the menu. And so this kind of explains our revenue formula a little bit. So we have our price times the growth rate, if you will, of the price increase, times demand, times 1 plus this demand elasticity. And then we had to incorporate a factor of the percentage. So if we took it up 2%, we were going to have to multiply the demand elasticity by 2. And so that's why we included the percentage price increase times 100. And I'll pass it off to Captain Mo.
We created a linear program model in Apple. It was a standard optimization model that maximized revenue. We had 76 menu items in our model, and we had 5 variables for each of them. One variable established the initial price. The others established the historical demand. Another set up the demand elasticity that was calculated. Another variable mentioned percentage price increase, which could vary, which is one of the things we were testing. And a binary variable, we used a binary variable to set a constraint so that not every menu item would receive a price increase, because that was also one of the constraints that was given to us. And our model recommended using a 5% ceiling for every menu item, so that's what we decided to go with. And this is our outcome. We came up with changing the prices on 19 out of our 76 menu items. Those are the menu items right there with your initial current price, our suggested price, and the difference. And as you see, we have about a 1.49% increase in the total overall menu price, which is within our limits for Brinker. Next slide, please. One of the things that Brinker requested from us was to create a way that they could, in the future, come up with price changes themselves. So we decided to come up with a pricing application, and the way we designed it, it was designed in Java. It's very similar to what happens in Apple in the background. We used the original revenue formula that we created for our Apple model, and this app allows you to put in up to 10 menu items. And the reason we decided to use Java is because it's portable. It can be used on any computer, just about anywhere, and this is a screenshot of what it looks like. As you can see, once the user executes the application, you can have a slot rows for up to 10 menu items. Put a menu item name, price, the historical demand, which is specified within our data, the demand elasticity, and you can also specify the number of menu items that you'd like to change. Once you hit submit, all the values in the right column change based off of the formula that runs in the background, which is very similar to Apple. And through numerous tests, it turned out that we got the same results as our Apple model, which proved that it worked correctly. So that is something that we also created for Brinker, so that in the future they can do price changes. Are there any questions, comments, concerns?
There it is.
So explain something that has like highest demand elasticity and how that would be handled in the model.
Okay, so the highest demand elasticity would actually be a negative one, given the lowest. And the way that is factored in is that our model realizes through our formula that if the value is greater, closer to positive or negative 1, that it will have a greater overall impact on total price, whatever changes you make. So it factored that into our formula with the percentage increases. So it was factored in there.
So something that has
the way that we orchestrated our linear regressions was that for every percentage price increase, we had our demand. And so demand elasticity shows how much demand goes down for every percentage price increase. And so the more negative, the less you want to touch it with the price, because they're not going to want to up the price when it's going to cause demand to go down.
We have our other team.
Did they talk at all about decreasing prices on some items? Maybe they could, they could hide a price increase in one item by decreasing some other things, advertising special, and then in the net,
Right.
still end up making no profit.
They haven't done that in the past because they don't want to take away this perceived value of the product. And so if they decrease the price, then now it's on sale and it's not a luxury restaurant anymore.
What software did you call from the Java program to solve the LP or the energy program?
When you say software, what do you mean?
What
Specific?
optimizer did you use?
We coded it ourselves. We created a system of loops that would go through all the data that was entered and use a similar model to what we had in Apple that would calculate the best values. And based off of that, it would spit out the correct values.
Okay. You just enumerated all the possibilities.
Yeah.
Thank you.
Other questions?